Do you guys watch The Office?
Yes, I do.
You do? Okay, sweet. Here we go.
Guys, welcome back to the channel. This is Rituraj and Wires, and I welcome you all to the channel. So today we are going to do dielectric and capacitors. So basically they are two different topics, but I have combined it in one because I wanted to make a connection between them so you can understand the logic much better than any other videos or topic you have been watched. Okay, so basically the first question I want to ask you is, do you know how an dielectric works? Like if I tell you that I just charge a dielectric, okay, and then disconnect it, okay, and then slide a piece of glass inside it. So what happens next is that the dielectric voltage and energy both will drop, but on the other hand, the capacitance of that capacitor would increase, or the dielectric would increase. So the question arrives that while the voltage and the energy goes lower, the capacitance increase. So why does more capacitance holds less energy? So this is apparent, I can say an apparent very beautiful concept that we're gonna answer today. So yeah, let's begin with that. And yeah, let me take you to the first topic. So yeah, we're gonna start with why dielectric changes everything. So when a dielectric slab is slid between the plates, the molecule gets polarized. So this positive and negative center separate slightly, creating tiny dipoles aligned with the field. This aligned dipoles create their own electric field opposing the applied field, and the net electric field inside the dielectric reduced by factor K. So what is basically a dielectric? If I say you in a simple language, basically a dielectric is, I can say, two metal plates, okay, in which we pass current over a circuit. Okay, so I can say that the dielectric is basically part of the circuit. Okay, and one is the plus part and one is the negative part. Once the current passes through it, we already know that the current when flows creates electric field around it. So we already have an electric field inside this dielectric plates. But what happened next is that the dielectric also induces some charges within themselves. So one of the dielectric might have the charge of plus and the other might have of the minus. So basically there is an electric field, applied electric field, and there is another electric field that is being produced by the dielectric. So the total actual electric field inside the dielectric becomes E naught by K. That is the equation here. Okay, so this is the simple basic meaning of what is a dielectric. So I can say that dielectric is just a conductor that polarizes. Okay, that polarizes, and this changed the whole concept of what we say an electric circuit. So that's why we need to go so deep inside dielectric and know what it is. Okay, so not everything else follows for this one fact, depending on what is held constant. Okay, like we say that sometimes the voltage is held constant when we charge the dielectric, sometimes it is not when we discharge it. So there are different topics that we different cases that we are gonna learn ahead. So yeah, the next topic is the one question that controls everything: is the battery still connected with the dielectric inserted? So this single question determines which quantity is fixed, and from that fixed quantity, every other quantity is followed by chain logic. So what quantity is fixed and what is not fixed determines how the circuit flows, how the current, the voltage and the energy in the circuit flows or in the dielectric. So basically, when the battery is connected, when dielectric is inserted, so yes, if the battery is connected when the dielectric is inserted, V is fixed, means the voltage is fixed, it is constant, battery holds V constant. So now when the battery is connected and the dielectric is also inserted, so now the voltage somewhat changes, but due to the battery is being connected here, so we need to maintain the constant voltage here. So for that, what does the battery does? So battery V not change, battery forces this. So how does battery forces this? So C K C naught. So by K, by increasing K, the K factor. So C equals to K epsilon naught A by D. We know the equation from this. So Q equals to Q, K Q naught. So increases by K. Everything increases by K, in which K can be multiplied. So E equals to E naught unchanged. Electric field is unchanged. U equals to Q UB. The energy is also increased, so U equals to half CV square, C is also increased, and but V is fixed. So this is the case when battery is connected, and when the battery is not connected, then Q is fixed, means the charge is constant. So when the charge is constant, no path for charge to flow, so Q equals to Q naught, unchanged, charges is trapped. C equals to Kc naught, increases by K, so C equals to Ke epsilon naught AD. So if you look here, so in both cases the capacitance increases, while the charge remains constant in the in the one in which the battery is connected, and the charge and the voltage doesn't remain constant in once the battery is not connected. Oh, sorry for this. So yeah, so E equals to E naught unchanged in the battery connected case, and in the battery not connected in case, so the electric field decreases because we don't have any charge flowing from it. So this is the obvious reason that the electric field would be reduced. And now U equals to U naught K, the energy also gets reduced. So connected V fixed, Q equals to U increase, disconnected Q fixed, V equals to when it is disconnected, so the charge is fixed and V, E and U decreases, and when it is connected, V is fixed, means it is constant, and Q and U increases. So this is the basic concept. Okay. So the chain logic, never memorize, always derive. The secret is to never memorize the table, instead run this chain every single time. So how does we run the chain? So chain for battery connected, V fixed. So V is fixed, battery holds it, right? V equals to V naught. So when the battery is connected, as I told you, when battery is connected, we have constant voltage. C increases, right? C equals to K C naught. Dielectric always increases C. This is the only thing that is same in the both cases, as I said you before too. Now Q equals to CV dot C increased, V same, means the charge is being increases. Q equals to Kc naught V naught and Kq naught. So Q increases, electric field is unchanged, and the energy increases. On the other hand, chain for battery disconnected, when Q is fixed. So when Q is fixed, C increase, right? C equals to Kc naught. V decreases. E also decreases because no charge flows, and U also decreases because our charge is getting reduced. Charge is fixed, means the capacitance is increasing, and capacitance here is inversely proportional to the energy. Okay, so yeah, that would be the case, and yeah, I hope you all get this. Let's move on to the next topic, that is the energy paradox. Where does energy go or come from? So basically, the first question that I asked before starting this video was, since the capacitance increases, but the energy decreases, so where does this energy go? So this is the answer to that question, that the most conceptually beautiful part and the most asked conceptual question in exams are case 1, when the battery is connected, energy increases, where does it come from? So U increases from U naught to Q U naught. Extra energy, where does it come from? For the equation K minus 1 U naught. So battery supplies extra charge in the form of delta Q equals to K minus 1 Q naught to maintain a constant voltage. So there is a change in the voltage. Okay, but since battery needs to maintain the potential difference in the circuit, so it forces some energy in it. Okay, so work done by the battery is equals to V naught into delta Q. So V naught K minus Q naught, and we have K minus U naught, means the energy. We have changed this into energy, U naught into 2. So we have 2 K minus 1 U naught. So wait, a battery does 2K minus 1 U naught of work, but capacitor only stored K minus 1 U naught extra. So where did the extra other K minus 1 U naught go? It was dissipated as heat in the connecting wires. Even ideal wire have this loss during the charge flow. Its fundamental result, additionally, dielectric is pulled into the capacitor by the fringe field, doing mechanical work. So basically, the question that I asked you before was, since the capacitance was increasing, however, the energy was decreasing. So why was it happening? Because some part of that energy, or we can say half of that energy, was being dissipated in the form of heat. So that was the actual answer for that question. Okay, hope you all get this. Yeah, case 2, battery disconnected, energy decreases, where did it go? So now, while the battery is disconnected, then also we are losing the energy. So where does this energy is being loosed on? So U decreases from U naught to U naught by K. Energy lost is represented by the equation U naught 1 minus 1 by K. So in the charge case, we have K minus 1 U naught, and in the uncharged case, we have U naught 1 minus 1 by K. Okay, so sorry, not the uncharged case, we have battery disconnected case. So the electric fringe field at the edges of the partially inserted dielectric exerts an attractive force, pulling the dielectric inward as it slides in. This force does mechanical work. Okay, so the electrical energy converts to kinetic energy of the dielectric slab and eventually to that heat through friction or damping when it stops. So basically the core equation or the core understanding of both of these cases is same. Where does the energy is being lost? In the form of heat. But in both are following two different processes. Okay, so in both cases energy is conserved, it just changes from the capacitor, it is not in a closed system, as I said. Yeah, so let's move on to the next topic, which is energy in capacitor and what is its derivation. So what does a capacitor stores energy? Why does a capacitor store energy? So charging require pushing charges against an increasing potential difference. So the total work done is stored as a potential energy in the electric field. So when I was teaching you about electric field in the previous video, please watch it guys. If you have not watched it, you might lose some concept or cannot gain some concept here, what I am telling you now. So basically when we need to charge an electric field or an EMF and battery, so we need to provide a voltage that is more than the EMF. Whenever the circuit have voltage that is being a voltage from outside that is more than the EMF in the circuit, then it is actually being charged. So for that case, we need something, we need a voltage that is being more than the potential energy in the circuit. So derivation, when charge Q is already on the capacitor, voltage is equals to V equals to Q by C. So work to add infinitesimal charge dq against this voltage. So dw equals to v dot dq, q by c dq. So simple work equation. So total work changing from 0 to q. So u equals to we are integrating q to 0. So qc by dq. So we have 1 by c dot q square by 2, and 0 to q we have q square 2c. So using q equals to cv, we have u equals to q square 2c and half cv square equals to half qv. Okay, so this is the basic energy in capacitor. Okay, so how do we define the energy in capacitor? So this is the equation that we're gonna use for deriving energy in capacitance, and I just made you understand the derivation also where it comes from. Okay, let's move on to the next topic. Okay, we have further more onto this. So when to use which from? So when Q is known and C is known, we're gonna use Q equals to Q square by 2C. So basically this part is for the numericals part. The theory part has been completed. This is specifically added for you to be able to solve different types of numerical and understand what type of formula we have to use in the equation. So when V is known, C is known, we will use half CV square. When both Q and V is known, we will use half QV quickest. Energy density, energy per unit volume in the field is defined as U equals to U by volume, means energy by volume. So we have half CV square by AD equals to half E naught V by D ka whole square by 1. So U equals to half E naught E square. So profound energy stored in the electric field itself, not on the charge. This idea extends to electromagnetic waves. Light carries energy in its oscillating fields. Okay, so this was about the energy density and how we're going to use the energy formula for capacitance. Okay, so the next topic is charge redistribution, the energy loss problem. When the two capacitors are connected together after being charged separately, charges flow between them until they reach the same potential. During this flow, energy is always lost, always, no expectation. So basically, no exception. So basically, we are talking about when two dielectrics are charged to different potential. So basically, what happens in an electric circuit? We need to have a constant, we can say a potential difference between the two sides of an electric charge or the two parts of an electric charge. So for making that possible, the same thing follows in the dielectric also. When we connect two different dielectric with two different types of voltage inside them, they need to cancel it out or make it balanced. Okay, so for that, the setup C1 charged to V1 connected to C2 charged to V2 or uncharged. So battery removed before connecting, charge conservation, charge cannot be created nor destroyed. So we have Q total equals to Q1 plus Q2 equals to C1 V1 plus C2 V2. So common potential after redistribution, V equals to Q total by C total, C1 V1 plus C2 V2, C1 plus C2. So basically guys, you need to know about these formulas. Okay, we have talked this before in the potential chapter or the potential difference topic. So yeah, you need to have some basic conceptual knowledge here. to understand this particular concept. I'm not gonna take you back to those potential differences concept, so I'm not explaining the where does the formula come from, but I can explain what's the logic behind the formula. So for potential, we have Q total by C total. So we have C1 V1 plus C2 V2, and C total is equals to C1 plus C2. So for opposite polarity, plus plate of C1 to minus plate of C2 when both the capacitor of different charges, so Q total equals to Q1 minus Q2, C1 V1 minus C2 V2, so V dash equals to C1 V1 minus C2 V2 by C1 plus C2. So energy lost, now we are talking about energy, so delta U equals to final energy minus initial energy, C1 C2 by 2 C1 plus C2, V1 minus V2 square, or we can say V square, delta V square. So always positive, always dissipated on heat radiation, cannot be avoided if V1 equals to V2, delta U equals to 0, no energy loss, charges already balanced, maximum loss when V1 and V2 are most different. So where does this energy go? Even with zero resistance wires, energy is always lost. The moment you can connect the wire, and infinitely large current flows for an infinite small time, energy is radiated as an electromagnetic radiation. A spark in real circuit, it is joule heat. So where does this extra potential or the energy goes from the circuit or the dielectric? So basically they are lost with the help of an electromagnetic radiation. So we are not dissipating the energy in the form of heat this time, we are dissipating in the form of, or radiating in the form of electromagnetic radiation to balance out the energy. So the energy loss is fundamental and unavoidable, so it is not due to imperfect wires. Okay, this is because of balancing and making the circuit overall work. Okay, the conservation of the energy, perfect. So the level 7, this 50-50 split, a beautiful result. So when a capacitor is charged through a resistors from a battery, the most common real world situation is that battery does work, W equals to QV or CV square. Energy stored in capacitor is equals to half CV square. Energy dissipated as heat is equals to half CV square. So exactly half the energy supplied by the battery is stored and half is lost as heat. So always regardless of the resistance value. So this is what we call the 50-50 split. So in this case, the battery does work, W equals to QV equals to CV square, as I told you, and energy stored in the capacitor is represented with the form of half CV square. So particularly the capacitor is being charged here through resistors from a battery, and exactly half the energy supplied by the battery is stored and half is lost as heat. So that is the actual case we are talking about when we were discussing about where the energy gets lost when two different types of dielectric, or we can say a dielectric in which it is being charged, or it is being charged and then disconnected and a glass slab is pulled into it. So where does this energy go? Where does this energy falls and go away? So this is the actual 50-50 split that we are talking about here. The 50% of the energy or half of the energy goes into heat form and the rest half gets stored in the capacitance. So always regardless of the resistance value. Okay, so yeah, let's move on to the next topic. Partial dielectric, the complete formula. Okay, we are now talking about the partial dielectric. This is one of the most important topic or exam related concepts. So when a dielectric slab of thickness T less than D is inserted parallel to the plates, the gap splits into two regions in series. So dielectric of thickness T, capacitance is equals to K epsilon naught A by T. So the dielectric of thickness T is represented with the formula K epsilon naught A by T, and air gap of D minus T is equals to air gap of D minus 2 is of capacitance is represented equals to E epsilon naught A D minus T by D minus T. So in series combination, 1 by C equals to T by K epsilon naught A plus D minus T by epsilon naught A is equals to 1 by epsilon naught A T by K plus D minus T. So this is when we have a different type of, we can say, slab thickness and the distance between them. In the case we don't have, or we can say a special case, conducting slab is K when K is infinity, we take C equals to E epsilon naught A by D minus T. So slab effectively reduces the gap. Position of conducting the slab doesn't matter, only its thickness matter. So as I told you, whenever there is a thickness between the dielectric, or we are talking about the thickness of the dielectric, so we need to take the first equation here, C equals to E epsilon naught A by D minus T plus T by K, and when there is no dielectric or the K, when there is no thickness, or we can say the K goes to infinity, then we will take this equation, C equals to epsilon naught A by D minus T. Okay, so this is the basic partial dielectric formula. Okay, now there is all the formula that we have learned in this particular topic with logics. So C equals to Kc naught, dielectric fills gaps completely. C equals to epsilon naught d minus t plus t by k, partial dielectric parallel to plate. C equals to epsilon naught a d minus t, conducting slab inside. V naught equals to C1 V1 plus C2 V2 by C1 plus C2, common potential, same polarity. When V dash, when C1 V1 means the dielectric are of different polarity, plus and minus. So C1 V1 minus C2 V2 by C1 plus C2, common potential, opposite polarity. Delta U, when the energy changes, so C1 C2 by V1 minus V2 ka whole square divided by 2 C1 C2. So energy lost in redistribution, U equals to Q square by 2C, half CV square, half QB, energy stored, and U equals to energy density, half E naught E square, energy density in field. Okay. Yeah. That was all for dielectric capacitance and its energy. Hope you all get this topic very well. If you still have any doubt, you can revisit the video back, replay it if you have got any doubt at a particular topic. If still it is unclear, please comment it out. I would be glad to help you out. So that was all. I would meet you in the next topic. Bye.
And now, folks, it's time to say goodnight. We sincerely appreciate your patronage and hope we've succeeded in bringing you an enjoyable evening of entertainment. Please drive home carefully and come back again soon. Good night.